its reading session today, and because today this happened basically. Alan Asperu, I'm really sorry about my pronunciation. The names, I don't know if you guys pronounce it Guzik. Probably that kind of comes from the Polish Guzik or something like this. But Alan, I hope it's fine if I just. I mean, I guess it's it's definitely a bunch of people that have. So this is from the Matter Labs team, I guess. I'm so new to all that stuff that I don't want I don't want to offend anyone. I don't know a lot of the people in the field, and but anyway, so there's this sudden stream of news where it's like so basically the idea behind these, I think it's about the concept that as quantum computers get bigger and bigger, we're getting into a trouble zone because we're not going to be able to basically kind of double check whether we're building them correctly. And I'm guessing that's the idea behind this, is to kind of use small machines to sort of aid the design process by simulating somehow the whatever we're building. And I have absolutely no idea what are the building blocks, and I don't know how this is gonna look like, but I thought I definitely want to read the paper. So here we are, and there's actually two papers I think referenced in here. One is for superconducting, I think. Is it increase the size of some modules? Yeah, so superconducting transmon processors. And this one is for photonic quantum computing, I think. Body entangled photons. Okay, so I doubt we can cover all these in one video, and I'm gonna kind of space them out a little bit. So I doubt I'm gonna even finish this one, but I just want to get into this because I think that's related to. There's definitely variational stuff in there, and so I just want to take a look at whether there's anything interesting for me, anything that kind of sparks a bit of extra love for variational quantum algorithms. Yeah, let's get into it. I mean, it's been a while since I did it. I need to put my face a little bit smaller, otherwise I can't read. Let's see, where is my mouse? I'll put myself in here. So, quantum computer aided design, digital quantum simulation of quantum processors. So there's many questions in here, right? So I'll put the links into the description. But for me, it's like, okay, so what is that you need to simulate to design a quantum computer? What are the building blocks, right? In the abstract, it says with the increasing size of quantum processors, the submodules that constitute the processor will become too large to accurately simulate on a classical computer. So it's the submodules that we're simulating or modeling. Therefore, one would soon have to fabricate and test each new design primitive and parameter choice in a time-consuming coordination between design, fabrication, and experimental validation. And test each design primitive and parameter choice in time-consuming coordination between. To circumvent this slowdown, we address the question of how one can design and test the performance of next-generation quantum hardware by using existing quantum computers. That's pretty cool. It sounds really, it's actually funny. Focusing on superconducting transmon processes as a prominent hardware platform, we compute the static and dynamic properties. Okay, so this is what we want to figure out. What are the static properties and the dynamic properties of individual and coupled transmons? So you're simulating the individual qubits or qubit setups. You see, my main interest here is I'm trying to understand how simulation is used in here, rather than, I'm not so much interested in the process and the design process of a quantum computer, but more on how is quantum simulation used for whatever purpose we've got here. So we show how the energy spectra of transmons can be obtained by variational hybrid quantum classical algorithms that are well suited for near-term reservoir computers. So the energy spectra of transmons. But why is this energy then? The point is, why is it something that would become challenging with bigger setups? We also numerically demonstrate how single and two qubit gates can be simulated via Suzuki-Trotter decomposition for digital quantum simulation. How can you simulate a gate? Cannot you just use the gate? I'm being totally stupid, to be honest. That actually sounds an interesting read. Then our methods pave a new way towards designing candidate quantum processes when the demands of calculating submodule properties exceed the capabilities of. So when the demands of calculating submodule properties exceed the capabilities of classical computing resources. So what are these properties? That's what I want to figure out. So first of all, I want to take a look at, just quickly fly over, so see what's awaiting. So there's an introduction. Then we've got some figures in here. We've got a candidate processor, so each dot is a transmon. So I think a transmon is just a qubit, or what is that transmon? In quantum computing, and more specifically in superconducting quantum computing, a transmon is a type of superconducting charge qubit that was designed to have reduced sensitivity to charge noise. Okay, so the transmon is actually the qubit. Okay. And so you've got a processor in here, and so this is, each of those things is a module, and then, so this is a transmon, this is the actual qubit. Okay, and then whatever is being used to read out stuff. So the transmon hardware simulation challenge. Transmon processor size achieved. Okay, quantum supremacy. Classically simulatable memory. Classically simulatable structured. Quantum simulatable transmons. Quantumly simulatable ions. I have no idea what this then means. The Summit computer is here. Okay, the Summit supercomputer is here. And so is this then Google's supremacy chip, or? Okay, so there's these in here, and then there's quite some text. Methods for quantum simulation of transmon processors. Okay, so here's so we'll probably fly through the introduction and come back to it later. Encoding of circuit Hamiltonians into multi-qubit operators. Variational quantum algorithm for multi-level systems. Refers to the qubit. So with the transmon Hamiltonian, so we're going to figure out a Hamiltonian for the qubit, and then rephrased in terms of the qubit operators. We can estimate its eigenenergies with high accuracy by employing the variational quantum eigensolver. A hybrid early implementation of have focused on estimating the ground state energy of quantum systems. The quantum device is used to prepare a candidate state by executing a parameterized quantum circuit whose parameter values are updated using classical optimizers. We know that. The classical optimization is guided by minimizing the energy expectation, usually estimated by averaging measurements from many runs of the same circuit. That's probably the best definition of what VQE is in just about 6 or 7 lines. The objective of VQ can be expressed as this. Okay. Sorry, I'm going to have to make my face a little bit smaller, just so I can. Yeah. Intrinsic has been generalized to estimate low-lying excited states in addition to the ground state. I didn't know that. I don't want to lose that. I didn't know that. In the later work, the original objective function in VQE is extended such that the kth excited state can be systematically estimated. This is crucial in determining high energy levels of superconductor transform systems, which are needed to generate high fidelity 1 and 2 qubit gate operations. So similar to VQE cost function, to the VQE, the objective for the kth excited state is so-called. I've never heard of this. What is this? Variable and deflation algorithm. So here we go, tangents. So what is this? Is this the paper? My face is bothering no matter where I put it. So quantum circuits prepares from individual states. So you do expectation of estimations of something, then overlaps. Okay. Okay, I might have to understand that first then. Okay, that's something to dive into. So this is some sort of generalized error accumulation, sampling the cost, destructive swap test. Isn't that the so isn't the destructive swap test the Hadamard overlap test? Why is then this a novel? From when is this paper? How do I know when was this first published? Or because I think submitted in May 2018. Okay, that's really recent. Okay, a couple of years, but so how come I didn't know about these? That's I haven't heard about these before. Okay, cool. Anyway, so it's a generalized. It's a different version of EQE. Okay, let's move on. For some reason, this is going to be needed. Suzuki Trotter simulation of quantum gates. In addition to the static energy spectrum, simulating dynamical gate operations is an important aspect in the design of quantum hardware. The relevant metric for a hardware gate is the gate fidelity, which is a quantitative measure of how well a control pulse transforms an initial state into a desired state, where U des is the desired gate unitary. Since hardware gates exhibit a number of imperfections, such as inducing leakage to high excited states, state evolution under the control pulse will not precisely implement the desired unitary. The exact time evolution of the initial state under the control pulse is written as these. Should probably use. Can I just use that to mark as I read? Yeah, but that's then I can't easily. Then I can easily switch back to the mouse. I gotta figure this out. Alt P, Alt M. Okay. The gate fidelity is then defined as the desired state. Okay, so it's sort of how. Okay, so this is the projection. Okay, yeah, so this is basically kind of what this is telling you is we're projecting these on these, and then we're taking a look at how, is it like that? And then, no, that's not a projection actually. What is that? I don't know. Okay, let's leave it for later. That's not a projection. An estimate of the average gate fidelity F over all the states in the qubit Hilbert space is obtained obtained by averaging the gate fidelity over sufficiently many hard random initial state samples. For the hardware gates applied in this work, we simulate the numerically exact state evolution in Qtip. Maybe it's time to learn Qtip. In order to estimate the gate fidelities and provide an exact solution benchmark. Okay, let me see that I understand that correctly. So the gate fidelities, whatever, and yeah, so this is somehow telling you we're comparing the state, the exact time evolution. So we're comparing the time evolution of so this is the time evolution of, you apply the pulse for a given amount of time to the state, to the initial state, and then you compare it to the destination or to the actual target state. We investigate the use of Suzuki Trotter evolution to simulate hardware gates on a digital quantum computer. With the first order Suzuki Trotter approximation, the exact time evolution under the control pulse becomes okay. Whatever that means. So it's the composition of something, and then where k is the number of Trotter steps, and this is the reduced Planck constant, and each exponential of a weighted Pauli string. Which is translated into the gate sequence on the digital quantum computer. Okay. The state evolution, I think all that is saying is that, yeah, you somehow make an approximation of which is approximated by kind of having the sort of gates and mixers, I guess. Results. This section is divided into two main subsections: single qubit design and 2-qubit gate. Single qubit design and 2-qubit gate design. Each of which can be then subcategorized in terms of two functionalities each, namely initial state preparation via the VQE and the VQD algorithms, and Trotterized evolution to carry out dynamical quantum simulation. That's the actual mixer part of things. By quantum computer-aided design, we refer to the use of quantum computers to generate the energy spectrum of the quantum device with high precision, as well as to simulate its unitary dynamics in order to facilitate the design of quantum processors. But why does this facilitate the design? That's my question. Based on the energy spectrum, we can analyze whether or not the quantum device... Okay, so based on the energy spectrum, we can analyze whether or not the quantum device being designed is robust against some external controllable or uncontrolled parameters. Okay, so the idea is to simulate, so you're trying to figure out whether what you're designing is robust against certain unexpected noise, or yeah. In addition, spectral information aids the design of desired quantum gates. I guess the design of the pulses, or so the transmon qubit with tunable external magnetic flux. The 4 lowest eigen energies are computed against the normalized external magnetic flux. I wish I'd understand any of these. As a first demonstration, we consider flux tunable transmon consisting of 2 junctions Qubit loop with junction energies, blah, blah, blah. The Josephson energy can be tuned by an external flux. This is that is threading the Qubit loop, and the entire system is going to the 4 data qubits accurately represent the low. So from numerical diagonalization, we determine that 4 data qubits accurately represent the low-lying states of one multi-level transmon, encoding the lowest 16 copper pair number states of the transmon. As we increase, so basically they kind of figure out that you need 4 qubits to simulate that. That's the point. When we employ the variation of EQ in order to estimate the same four lowest eigenenergies, our method relies on absolute. Okay, we'll take a look into this right now. Evolution. In addition to producing the energy spectrum with high energy accuracy, VQ and VQD prepare the initial states in order to evaluate the performance of the trotterized beat Philippe gate operation. We prepare 3000 hard random initial states, sample from the block sphere spanned by and evolve them both numerically exactly and the average gate fidelity is found to be these. Okay, so the environmental population of the ground state can be increased by further optimizing the gate parameters. But how has this been done? I guess there's might be some appendix or something with 2-qubit cell design. So two-frequency tunable transmon coupled to your capacitor. The lowest 5 excited state energies with respect to the ground state energy are plotted as a function. The design of a device that is capable of quantum computation requires 2-qubit simulations en route to scaling to a large processor size. Although we have already found the energy spectrum of an individual transmon, the spectrum has to be updated when 2 or more transmons are coupled together via capacitors, such as in the circuit figure 4. I'm just reading roughly through these to estimate eigenenergies of the transmon system. We can apply algorithms here. The ansatz used for simulating 2 transmon qubits comprise 2 blocks of the 4-qubit circuit template used in the single transmon case, followed by an 8-qubit circuit template. D3. Okay, so there is some sort of appendix, I think. That's where probably I should look at, because that seems to be a bit more of a summary. After states are labeled. Okay. After performing the VK, there are 2 commonly used 2-qubit gates for capacitive coupling: C phase and swap, and I swap. Each of them is implemented by tuning the system to a different avoided level crossing. The first avoided level crossing between the states 1, 1 and 2, 0 enables C phase gate, while the second avoided level crossing I swap. For a proof of principle numerical experiment, we carry out digital quantum simulation of the more common C-phase gate operation, which features less leakage to undesired states. There are 2 means to realize the gate, one via an adiabatic sweep of the external flux. This is tougher than I expected. The performance of the exact... It can also be applied to more advanced protocols leading to fast and high fidelity gates. In addition, we remarked that we implement gray encoding scheme subsystem-wide, such as a combined 2 transmon system is given the tensor product of 2 single. What is the gray encoding scheme? Scaling up to a multi-qubit submodule. Okay, so so the paper goes through how to simulate 1 qubit, how to simulate transmon, how to simulate 2-qubit system, so a 2-qubit cell, or how they call it, and now C is scaling to a multi-qubit submodule. So this is like what we saw in the beginning with like 4 dots, and that was, I think, one of those things, right? Based on a study of digital quantum simulation, a single and 2 transmons, we anticipate that the presented to simulate next generation are available application for NISQ. In the case of a transmon chain submodule, such as the one in Figure 1, variation algorithms would shed light on unwanted crosstalk arising from spurious capacitances between any or all the transmons on the submodule. Such interactions can be gleaned from the static energy spectra that variational algorithms provide. The relevant metrics for experimental suitability of the variational algorithm are the number of data qubits, circuit depth, and gate count required to simulate an M-transmon processor sound module, both for near-term quantum computers and for intermediate scale, partially error-corrected architectures, gate errors, and those simulated. In addition, algorithmic runtime is closely linked to Okay, so in order to simulate M-transmons, the circuit ansatz used for the two-transmon simulation in section 3b can be naturally extended. Each transmon is again encoded in 4 data qubits using the gray code, such that the total data qubit count scales linearly with M rather than exponentially if one were to use a classical computer. The qubit count can be reduced by exploring different encodings or by using less data qubits to represent transmons that are expected to be less relevant for the spectral region of interest. We place 2 layers of 4 qubit ansatz blocks at the beginning of the variational circuit, connecting each set of 4 data qubits that encode a single transmon. The next 2 block layers then connect 8 data qubits and continue to add pairs of ansatz blocks that double the included number of qubits. The final block pair is a 4 times m qubit ansatz that connects all the qubits. Okay, we'll go to the figures in a second. We determine that the gate count and depth of the variational circuit scales favorably with the number of transmons. Unlike stationary simulations, the dynamical gate simulations are beyond the reach of near-term devices. Unlike stationary simulations of the spectrum, the dynamical gate simulations are beyond the reach of near-term devices. The reason is the large number of 304 and 152 entangling states, upper bound per single Schroeder step, to simulate the single qubit bit flip gate and the 2 qubit C-phase gate, respectively. The number of gates in the single qubit simulation is larger than the 2 qubit gate simulation. The number of gates in the single qubit simulation is larger than the 2 qubit gate simulation because of the drag scheme, in which the Hamiltonian is a function of projection operators instead of sparse matrices. So is this saying that the dynamical gate simulations in such an M transmon submodule is not doable with NISQ devices? The gate upper bounds are estimated by canceling adjacent gates. The gate count can be principally reduced by tolerating a higher Schroeder error. Okay, conclusion. The best quantum processes today are already too large to be simulated on any existing classical machine, and they continue to grow at an exponential pace. If one hopes to capture the behavior of design primitives and submodules that grow with processor size, future quantum processes will have to be simulated on quantum computers. In this work, we have developed and simulated a detailed set of hybrid classical units that can be used for quantum computer-aided design. With the use of variational quantum eigensolver and variational quantum deflation algorithm for near-term quantum processors, we numerically simulated quantum circuits on 4 and 8 data qubits that encode a single transmon and 2 capacitively coupled transmons, respectively. Errors incurred from running these algorithms are small with respect to the dominant system energy scale. In addition, we were able to prepare transmon eigenstates and pinpoint avoided energy level crossings, which are then used to simulate dynamical 1 and 2 transmon hardware gates with state-of-the-art fidelities. The Suzuki-Schroeder gate count suggests viability of performing these dynamical simulations on intermediate-term quantum, and Schroeder errors scale favorably with Schroeder step size. Our work indicates that quantum-aided design enables exploration of circuit parameters within the quantum processor submodule without fabricating and redesigning physical hardware. Okay, that's the value. Okay, I get it. So the value is you don't want to have to fabricate something to actually test it. You want to simulate it upfront. In order to have further design control, One may combine our proposed scheme with classical computation methods for superconducting circuit design and simulation from both classical and in addition, our methodology of encoding multi-level quantum hardware in data qubits on this case framework that is readily applicable to trapped ion, neutral atom, photonic, and other systems. So the photonics one is here, right? So quantum simulation of optical elements. Boston sampling. Here we got some circuits actually. So this is a way to simulate a beam splitter. So this is an ansatz for a beam splitter, an ansatz for a photon source, a dove prism, mirror, mode shifter, phase shifter. Shorter steps. Okay, let's go back to this. This is for later, I guess. Cool, and that's it. And then I guess now comes the actual qubit design stuff. Okay, so the actual ansatz. Why is this so slow? My scrolling is lagging. Physical qubit Hamiltonians in the charge number basis. Traditional flux qubit C, shunted flux qubit. Encoding quantum operators into Pauli strings. In order to represent the superconducting circuit or any other type of D-level bosonic quantum hardware in terms of qubit states, we convert the eigenstates of the number operator n into the computational basis states of k data. What? Appendix D, variational ansatz for VQE, VQD simulations. Scaling of the variational ansatz with transnom number. Okay, so this is the qubit encodings. Standard binary gray code and unary of elementary operators used in this study with the truncation of D16. Gray code. What is gray code? A lot of unknown stuff in here. Gray code. Gray code is an encoding of numbers. The adjacent numbers have a single digit differing by 1. The term gray code is often used to refer to a reflected code, or more specifically still, the binary reflected gray code. Adjacent numbers have a single digit different by 1. Okay. What are those y? The cosine and the sine here. Here we go, some circuit. L layers. So what is this? B. Okay, so the 8 qubit ansatz. So those are the building blocks to simulate those components. The 4 qubit ansatz. I'd like to understand maybe how is this constructed? How is this ansatz constructed? It's funny because it starts with, it's not the typical design of an ansatz, or at least not what I've seen so far, because it starts with a layer of X. Oh no, actually, of X? No, that's a funny design. What is XX? It's what is this gate? I have to understand what is this. It's funny because it starts with like XXX layer. It seems like it starts with a mixer layer, which is kind of weird, right? I mean, if you would kind of you wouldn't apply that multiple times, but well, you wouldn't append these, but so maybe that's the first thing to figure out. So we've got like, okay, we'll talk about open questions right now. We'll talk about open questions right now because we need to definitely dive into VQT, and then we need to understand how the ansatz is built. Parameters kind of circuits used to compute spectra of superconducting. And what is the spectra of superconducting circuit architectures? What is that? Is it just the? Good luck finding that. It's the energy. I don't know. 2 unit layers of these 4-qubit ansatz works. The 4-qubit version of the circuit structure used to simulate a single transmon. 2 unit layers of these 4-qubit ansatz were employed in simulations. 2 unit layers, okay. 2 unit layers. To simulate 2 capacitively coupled transmons shown on the left, we will leverage the pre-optimized 4-qubit ansatz layers from single, but you see you're using them, so you actually do put them one after the other, so I don't get what's the point of starting with 2 unit layers of these 4-qubit ansatz were employed in simulations. To simulate 2 pen an 8-qubit ansatz block to capture the interactions between the 2 transmons. Okay. So this is applied twice per qubit, and then this is supposed to sort of simulate interactions. Okay. Yeah, makes sense. What are XX gates though? The final block is also repeated in order to simplify the analysis. Oh, sorry, that's something else already. It's not the. By using results from single trans simulations, this avoids using a greater number of costs. By using results from single transmon simulations, this avoids using a greater number of costly 8-qubit ansatz layers. What does it mean that the number of entangling state scales quadratically with the number of transmons, which is 0 for a midterm algorithm? Here we discussed the scenarios in which XX gates. What are the XX gates? It's an Ising gate. It's a Kaplan gate. I've never. What is this doing? Oh, I don't know. What is this? What is this doing? The Ising gate is a 2-qubit gate that is implemented natively in some trapped ion quantum computers and is defined as this. But what does it do? Okay, so we need to understand what is the Ising gate doing intuitively. I should make a list of those things. Can I open the notebook or something? Notepad. So understand VQD, understand XX Ising, what's it called? Coupling gate. Understand the design of the ansatz. So this would be QCAD. Scenarios in which it can be performed many different pairs of qubits simultaneously. Cases when the blocks are sequential, they can parallel if there are different blocks. We start with the first scenario, which is inspired by the experimental work by Zizek et al. That suggests that simultaneous access gates between arbitrary pairs is an emerging capability on ion trap processors. For a single block, there are always 2 layers of single qubit gates. It seems these gates are somewhat native in ion trap quantum computers. We then need to find the minimum number of steps to apply access gates between each pair of qubits. This step, whatever. What am I even reading? Many level transmon in the drag scheme. Unitary gate operators. Unitary gate operation for a single transmon system is non-trivial, and it ought to be discussed briefly here. In this section, we derive the driven transmon Hamiltonian that is simulated in section 3a for the bit flip operation. For correctness, we focus on single transmon bit flip gate or NOT gate, which can be attained by driving the resonator line capacitively coupled to the transmon. The way to realize the NOT gate in general is to drive the two lowest energy levels with an external field that is resonant with their energy difference. However, the transmon level. No, those are too technical details for me, but I guess they explain how you really implement the NOT gate. In order to overcome this issue, the derivative removal seems that the two lowest energy would populate high energy levels, thus reducing the gate fidelity. In order to overcome the derivative removal by adiabatic gate scheme is applied, and the corresponding result can be seen in the main text. The idea of the drag scheme is to use 2 slowly varying quadrature controls to instantaneously cancel leakage to undesired. This is really low-level stuff, man. This is really low-level stuff. But I'm trying to kind of, cherry pick the kind of higher level ideas here for, where is simulation used and the combined system. And okay, so here they basically say we apply this fancy technique and we get a combined system Hamiltonian. It's a Hamiltonian for the system and the drive, if I understand this well. So the actual part, yeah. So the whole system. 1 transmon, resonator, interaction, and drive. So you're adding all these. Like you get this fancy so you do some fancy math and you get to unitary evolution. For leakage free, we require Gaussian modulated envelope. This is the domain expert part, Strossen says that it starts and ends at 0. The parameter TG refers to the gate time. So the Hamiltonian that we use to digitally simulate the bit flip gate in our numerical experiment seen in figure 3. Equation E5. Okay, so this is it. So this is what they use to simulate the NOT gate. So again, this is the Hamiltonian of a system that kind of is supposed to create the not gate, because you want to simulate that. That's pretty nuts. That's pretty nuts. Average gate fidelity. Okay, there's a lot of work to do. Woo! We got to the end. There's a lot of work to do, but I like it. So we need to understand VQD. We need to understand the Ising gate. We need to understand the design of the ansatzes. We need to understand. So for the sort of the for the static part, and then also for the dynamic part. So I want to understand how they roughly for the dynamic part. So these are, I guess, gates. You want to see what kind of, I guess the idea is you want to see what kind of fidelity a given design would give you, right? And so, and here you want to know, I don't know exactly what you want to know here though, to be honest. Yeah, but so we've got 4 parts to explore after this. This is going to be a complicated one, but I hope, I kind of think I get the general idea. So the general idea is you've got basically the challenge that you're designing the different parts of a quantum computer, and so and so you wanna kind of simulate the properties of what you want to design, of a particular design, without having to fabricate it first, right? And kind of test it experimentally. So you're saving time and money there. And then the challenges come into, okay, so how do you simulate each of these things, right? So how do you simulate each of the small systems, and how do you calculate the properties that you want to, what is it that you want to find? I mean, what is it that the simulation is gonna tell you? That's what I still maybe not clear. Where I want to go back to one part of the paper where they said, where I was reading that that something scales linearly instead of exponentially. The resource requirements for such classical simulations scale exponentially with the number of simulated hardware qubits. Yeah. Energy levels. These are transient qubits for qubits computation are low between the energy levels, and inclusion of additional states beyond the computational states is important to understand the device characteristics and implement high fidelity control pulses. So interesting. As a result, classical simulations of quantum computing hardware are limited to a small number of qubits, even when employing the most powerful supercomputers. With the rise of quantum processes. Okay, so we wanna basically do that. So that's what I'm gonna do. That's what I'm gonna do maybe in the next videos, I guess. I want to start digging into VQD. I want to start getting into what the Ising gate is doing and design of the ansatzes, and then kind of what's the whole purpose of the. Need to put all the pieces together. Or how to use cat, QCAT. Is the Ising coupling gate, and why is this used and not something? At that point, I'm just already just bothered by curiosity. Final block pairs. All blocks are extensions of the 4-qubit ansatz with single layers of X and Z rotation gates at the beginning and end, and Mulmer-Sørensen gates between each pair of qubits. So this is the Mulmer-Sørensen gate. Okay, so what is... I wanted to dig into this already for quite a while. So what is this gate? The MS gate is a 2-qubit gate used in quantum computing. It was proposed by Klaus Müller and Anders Sørensen. To implement the gate, 2 ions are irradiated with bichromatic laser field with frequencies blah blah blah. The above can then be shown to produce a universal set of gates. The Mozart gate has the advantage that it does not fail if the ions were not cooled completely to the ground state. It does not require the ions to be individually addressed. An experiment that was done by PC where this gate was used all 4 Bell states. What? You can implement Qubit's algorithm with this gate? I gotta take a look at this. That's gonna be a long series. I love that. I love the fact that I found this paper. What? MS gate. Reverse algorithm. What is this? Probably should search for this paper. Spin dependent force is trying to. So what is the? Okay, but is this the same? Is this gate? Where else can I find more about these? And is equivalent in something like this. Where can I even find anything about this gate? Control 2 qubit. Can I just search for this? In ion traps, the qubits are naturally coupled by collective vibrational modes, generating a sideband structure. The Möller-Sørensen gate is a single-step 2-qubit entangling. It's a 2-qubit entangling gate. It's a 2-qubit entangling gate, driven by 2-tone 2-photon excitation. Something to me. It looks like Rabi driving. It looks like Rabi driving of a single qubit coupling the. But what is it doing? Maybe I should just create the gating quirk and try to figure it out, right? Because that's what that's what it's doing. It's like I'm unable to read that and come up with an understanding of what it's actually doing. Circuit design for design, I think. What is this paper about? This is literally a paper designing Grover's algorithm circuit from 2002. Okay, I'll just trash that. Why doesn't anyone explain this gate a bit better? How am I even going to search for this? So if I take, if I take quirk and I try to implement that, what am I going to get actually? Quirk. I'm probably way off what I should be doing right now, but so as can I do? I don't know if I can do that. Say pi. I can do that. Yeah, pi divided by 2. Minus I times sinus sinus pi divided by 2. 2. I guess now we've got 0 here and this here, and so by this. Okay, and now here's a 0, and this goes here. And then we have it's the same thing but flipped, so that's like minus I times sinus, and this is sinus cosine. And now the last one is this. But minus I times sinus, and this is cosinus. Okay. Yeah. Is this what the gate is doing? It's X. The pi rotation. Thus. Okay, it is an entangling gate, indeed. Interesting. So it generates different entanglement states between 2 qubits. Huh. I guess pi is the wrong angle though. Or for me to see pi divided by 2. So what if I just use pi? So, oh man. make gate. Oh, look at this. I actually have the. So what if I just use pi? Maybe it's gonna be a bit more understandable. And we're gonna call ms pi. Pi. Oh, I called the other one pi. Pi. PP. No, it's still not doing what I imagined it would do. I would imagine it would create an actual pure entanglement in here. But it seems like it doesn't, so. What is E? Ah, okay, so it does. So it does take. Okay, so it does take you. Can I not use the? Can I use the pen? Oh, P. No. Okay, so it does. So it takes, for example, if it's 0, 0, it takes me to 0, 0 plus I 1, 1. Okay. Interesting. That's what it does. It's almost like it creates an entangled state based on a seed. Yeah, it's interesting. Because if I think about a typical way to create entanglement, where you just you just go and use the Hadamard gate and you do this, right? And so in here, if I have a seed of 0, 0, let's say 0, 0 takes me to basically 0, 0 plus 1, 1. If I change these to be 0, 1, it just, okay. Yeah, it does actually. So this takes me 0, 1 takes me to 0, 0 minus 1, 1. So it also behaves in a similar way, right? So this takes me to 0, 1. So this takes me to 0, 1, 1, 0. 0, 1 plus 1, 0. And the other one, sorry, and this is 1, 0. And then 1, 1 takes you to 0, 1 minus 1, 0, right? I guess that's what it does. Does it? Sorry, minus 0, 1. Minus 0, 1, minus 0, 1. So it does give this kind of configuration, so this gate. But then wouldn't I be able to? That's interesting. I've never seen an answer that's being created like this, to be honest. Okay, so this is just a similar entanglement, but it's with a complex phase in here. That's nice. That's neat. Okay. So now the question, so I actually ticked one of the boxes maybe, if this is the case. But now the question becomes, why is this a good answer? Why is this a good answer? Because maybe that's why you've got. I still don't understand why this layer is here. But then I get it. Those seem to be all the possible. Or maybe I should take a look at this. So these are all the possible combinations of qubits you can entangle. So this block is responsible for simulating entanglement. Okay. And here, I guess you're picking 2 different dimensions to move around, rotate around. I'm not entirely sure why this is needed. But now I get these. These are basically entangling gates. In a lot of ansatz, I just see a control Z is being used. So what's the advantage of a control Z versus like an MS gate for an ansatz design? Okay, that's maybe a next question. So here, what is the advantage of an MS gate versus a control Z gate for entanglement ansatz? Cool. Yeah, that's interesting. That's definitely interesting because the control Z also creates entanglement, right? So if you take a look at the QE at the QAOA ansatz, it's kind of what you have, right? Ni hao. What's up? Model ansatz. Come on. Ansatz. Yeah. Yeah, you see? With the control Z gates. Yeah. And Y rotations and Z rotations. Okay. Is it just is because there's Y rotations and Z rotations, what will be the difference of the X rotations and Z rotations, and that would still, yeah, that's okay, that's an open question. So that's what I commonly see in ansatz design. Yep. Cool though. At least, I mean, I'm definitely not gonna understand the details of how to build a quantum computer, but I want to understand what are the pieces you're simulating and why those specific choices are made. I think that's going to be helpful, and that's going to just be I think, educational. I hope. Cool. That was a long session, but I liked it. Stay tuned for more.